So I think you've heard that the future is already here. It's just not evenly distributed. So if you want to know about the future, like let's say 2020, actually that's not that far in the future anymore, maybe 3 years, or 2025, all you have to do is look sort of in the corners of what's going on today. And in fact, at this conference, you're going to be doing quite a bit of that. And you get a pretty good idea about where the future is going to go. Let's, however, go back a ways, maybe 20 years or something like that. And the first thing I want to talk about is scale, getting big. Because actually 20 years ago, things that felt big are really small today. And things that are big today have scaled in a particularly interesting way. They've scaled broad rather than tall. So if you were a penguin in South Georgia Island, all these pictures, by the way, were taken by my husband, Tom, who's a great photographer. And this is king penguins, and when they don't have enough space, they go out to sea. You know, they don't climb up more mountains. And so let's talk about what happened 20 years ago in 1996. What was the state of what was going on there? Most of the software development at that time was business software or control software. When I did software development, I was a process control engineer. I controlled great big pieces of equipment with my code, which I'm biased, but I think that's the best software in the world. And so I wasn't involved in this stuff that they call IT. But most software was done, at least the literature, to read the literature, was all about great transaction processing, mostly in enterprises. And this is just as the internet started to gather some software. I remember in 1999, somebody was saying about how fast the software, how big software was and how long it took to change. We're talking a release of a year was fast. I can remember reading in Computer World that there are some teams out there that have learned how to deliver software in 6 months. Can you imagine that? So it was really slow to change. And I thought, you know, there's an awful lot of new software that's come. This is 99, and I was talking to some colleagues, and it's called the internet. You know, that's a lot of software that's been developed in the last few years. And they looked at me and said, the internet? That's not software. Yes, it is, but it's different kind of software. So back in 1996, we thought about transaction processing as, here's a database, an ERP database. When I was doing process control systems, I followed one of my systems to a manufacturing plant, and I headed up the information technology office in the manufacturing plant. And we did something called MRP, called Material Requirements Planning, which meant we planned all of the different inventory movements that happen through the plant and all of the production workstations. And that eventually expanded to the whole enterprise, so it got to be called ERP, Enterprise Resource Planning. And Enterprise Resource Planning was centered on a database, the corporate database, the one single thing which sort of integrated all of the applications in the enterprise, and still does, actually. And it sat on a single server. And, well, why is that? Well, you know, there's this theorem called the CAP theorem. You may have heard of it, which basically says if you've partitioned your database onto different servers, you can have one of two things, but you can't have both. You can either have it available instantly when you want it, or you can have it consistent. You can have consistency of across a transaction, the whole transaction or none of it, but you can't have both. And so, because the database was the thing that provided us with both the availability and the consistency of transactions, we had to have it on a single server. So if you look into the late 90s, all of the databases sat there, the corporation enterprise sitting on one big computer and integrated through that computer. And that was like the only way to go. But then, along came Google, and suddenly there was a whole bunch of data that didn't fit on one server anymore. In fact, if you have 1.3 billion pages, this is about 2001, it's just not going to work. You have to go across a bunch more servers. You have to figure out how to do that in a way that allows you to respond very rapidly. So there's two ways. You can go big or you can go wide, okay? Tall or wide. You can either get a much bigger computer, and interestingly enough, in about 2000, I think it was, Amazon was sitting there with a big front end, one big front end and one big back end, that single database. And at every holiday season, they absolutely couldn't handle the transaction volume anymore. And so you know what they did? They got a bigger computer. And do you know what happened? Okay, if you know anything about queuing theory, you go to bigger batch and you get slower. And they got slower. So they said, well, that's not going to work. So this is Grace Hooper. You've heard of Grace Hooper? She's the sort of, she's the one that designed COBOL and all of that. And she said, if one ox couldn't do a job, they didn't try to grow a bigger ox, they used 2 oxen. When we need greater computer power, the answer is not to get a bigger computer, it's to build systems of computers and operate them in parallel, managed by software. That's the whole concept of scaling out rather than scaling up. So you get more computers, and you figure out how to deal with the fact that they have problems. So for example, here's one of the first hardware racks from Google in 1999. It's in the Computer History Museum now. And when I first heard about how they were storing all of those billions of pages, I was rather surprised. They used this really cheap stuff, and they expected it to fail, and they kept multiple copies of stuff so they could just toss out the stuff that fails. Like, what a good idea. And they managed it with software. So the concept was actually kind of radical at first, but really the only way to go. So the whole idea, if you're going to search the whole internet and you're going to provide responses instantly, is that not only do you take your hardware and spread it out, you have to do the same with your file system. So here is the early paper in 2003 on the Google file system, and same concept. You take little tiny chunks of your file, you throw them all over the place, you make sure you got good 3 copies of everything, and then when one of them dies, that's okay, there's 2 more, you just sort of throw out the stuff that dies and regenerate it. And it's that whole concept that your whole underlying system is fragile, no problem. You manage it and you have multiple instances so you can deal with it. And then, of course, you've got your data that you have to search instantly scattered all across these files. And a year later, in 2004, they came out with the paper on MapReduce, which became the basis for Hadoop, which sort of spread through took from 2004 to maybe 2010, 12, before it emerged suddenly as this wonderful thing that everybody could use. It took a long time to get Hadoop from handling just a few files on just a couple of computers to something that could deal with massive amounts of data. And it was done out of the Apache open source project, and I think it was Doug Calfati who worked on it, went and worked at Yahoo. He was hired by Yahoo because they decided maybe they better go to this MapReduce thing too. And between the various big companies in Silicon Valley at the time, the whole underlying structure of Hadoop was developed over about a 5 to 8 year period. And there was an awful lot of sharing because Doug decided that it was going to be open source and he would be happy to work for Yahoo, but had to be open source. And it's that thing that we do in the software engineering world. We share our knowledge so that it can grow a whole lot faster. And I don't think without the sharing of all of the different knowledge of how these file structures and databases work, I think if these companies kept it proprietary, we'd be a long ways back from where we are now. So that's one concept. You scale out with a file system. When you look at your architecture, it's the same concept. You might think you've got a big monolithic database, But if you have a big monolithic database, you're not big. Because if it's all in one spot, it's actually pretty small. In order to really get big, you have to scale out. So let's go back to that Amazon in, as I said, about 2001. And there they are with a gazillion transactions, and they had to handle all of these transactions all at the same time. And the first option was to scale up. Okay, so take a single transaction. Let's say it's four things. There's shopping cart, browsing, shopping cart, payment, and fulfillment. Okay, and if you take a look at that, then you can scale the whole transaction, maybe even across in regions, different computers, if you want to. But if you want to scale out, you scale differently. You take your transaction and you say, you know what? I'm not going to let the database handle it anymore. I'm going to handle that transaction all by myself. So I have my 4 different services, say the browsing and the purchasing and the fulfillment and the payment. And if I have a few that are bottlenecked, I'll just scale out at that small area. It turned out to be pretty much the way that people have figured out how to scale since, as in they did microservices long before a lot of other companies. And they did it because the idea was, if we are going to have to handle this many transactions, we're going to have to think differently about how we scale. Amazon had a meeting of the executives after one of these almost disastrous holiday seasons. And they said, how are we going to deal with this whole thing next year? And they came to a conclusion. The conclusion was, we have to communicate better. Have you ever heard that? Kind of sound familiar? I think it's kind of a cop-out. If cop-out is a good word in English, it's just, I don't know what you say in German for cop-out. It's, what's a good translation for that? Out? Did you guys hear him? So it's an interesting excuse, but it isn't the solution. In fact, I hear the same about training. Oh, if we just had more training. Well, Jeff Bezos says, what we need is less communication instead of more. We communicate too much. It doesn't scale. Not at the scale that I intend to scale this company. And so the idea is not to communicate more. The idea is to communicate less. And you do that through an architecture which doesn't force people to have to communicate. So they decided that they were going to break the company into much smaller teams and put those teams on chunks of software that didn't have dependencies, so they wouldn't have to talk to each other. They were relatively autonomous teams, as autonomous as they could make them, without dependencies as much as possible. And they were what Jeff Bezos calls a 2-pizza team. They could be served lunch with 2 big Seattle-sized pizzas, yes. So maybe 8 people or something like that. And they own the whole service, cradle to grave. Idea, design, testing, deployment, everything. Monitoring and production. And so you have these 2-pizza teams that deal with all of those transactions coming through. They might own the shopping cart service, or they might own the recommendation service, or something like that. So that concept of scaling out rather than scaling up only works if you are using software to manage the stuff you used to have dependent upon the hardware or dependent upon the database. So let's go on to infrastructure as code and continue our story. Because I just talked about scale out, and I want to talk about infrastructure as code as another important, hugely important thing happening in software engineering. So have you heard of Conway's law? Most of you have. For those who haven't, it sort of says your organizational structure and your system architecture are going to match. No matter how hard you try not to, your architecture is going to drive your organizational structure, or your organizational structure will drive your architecture. Now, if we go to Amazon that then broke up into these 2-pizza teams They now have an organizational structure that drove their architecture. So what happened is these two-piece teams were supposed to be autonomous, yes, and so they had autonomous teams. And autonomous means independent deployment. That's what I'm going to define it as. It's not I get to make my own decisions, it's I get to deploy without having to talk to all the other teams. That's what it kind of meant there, which basically created havoc in operations. If you're in ops and all of a sudden you had 50 million teams trying to deploy all independent of each other and you hadn't actually handled all the dependencies, this could be a real nightmare, and it was. So Chris Pinkham, who was the vice president of infrastructure, thought about Amazon and thought about the problem and said, you know what we ought to do? We ought to have self-service deployment for development teams. You know, instead of dumping all their problems on us in ops, we ought to let them handle their own problems. We'll just give them the code to deploy by themselves. And he said, you know, maybe we could even sell this capacity. And if you know anything about Jeff Bezos, who was the CEO there, you know that if you have something he might be able to sell, he was truly interested. It took a little while for that interest to sort of percolate up and then down again, and meanwhile, Chris Pinkham went back to South Africa where he grew up. And when they finally got to his idea and said, let's do it, they chased him down in South Africa and said, say, why don't you put together a team there where you want to be and see if you can't make this idea work? So he did. He assembled and led a team, and in 2 years, they came out with EC2, Elastic Compute Cloud, which was launched in 2006. And as they say, the rest is history. Here we are 10 years later, and Amazon Web Services is making like about 10 billion US dollars a year or something like that, and growing. I used to say $1 billion a quarter, but it's even more now. And it all came from this concept of these independent teams that could do something that really could be separate. So if we think about that, then I want to propose that there's a cloud in your future. And I don't care if there's regulations to keep it from being that. If you're in a bank or if you're in a telecom or if you're in a medical area where actually right now there isn't a cloud, there will be. And the reason is because from economic point of view, cloud is cheaper. Generally speaking, most clouds are cheaper, more stable, more secure, and more expandable by far than most on-premise data centers. So if your IT center is about cost, and it becomes possible to overcome those issues of regulation and things like that, then there will be a cloud there because it will just plain be cheaper, simpler, more secure, and so on. Even if it isn't today, it's almost certainly going to be. And then there's, and then there's the technology. So if there's let's say you're in a bank, okay? Banks currently are all on-premise or sometimes hybrid, and the stuff that really, really has to be stored on-premise stays there. But right now, GE has a cloud called, Predix, that's right, called Predix, which is an industrial cloud. It can, for example, manage electrical grids. It was the underlying technology that managed the electrical grid in London during the Olympics to make sure that none of the venues lost power during any of the events that were there. Now, if you can put IoT devices on electrical grids or aircraft engine, which GE does too, and send that information through the cloud to some place, you have to be able to do it securely. That's what they do. They do this stuff with a high degree of security, and they do it matching whatever regulations of the governments that they're working with. So their cloud is probably quite secure and matching regulations in industrial areas. And they have just put a medical device cloud together, which passes at least all the US HIPAA regulations, which people said couldn't be done, but they've figured out how to do it. So if you're in a bank, I'm going to bet that in a few years, some bank out there will come up with a banking cloud which matches all of the regulation and security requirements that you currently think can't be matched. And then you go back to that cloud will probably be cheaper, more stable, more secure, and more expandable than what you happen to be working with right now. So the economics of it will be incredible. So I bet there's a cloud in your future. And not necessarily a hybrid cloud, because people are doing hybrid clouds, but the right use case for hybrid clouds that really makes it the right thing to do has yet to be discovered. Now, if you're going to a cloud, you're going to understand that the applications which are designed with traditional data architectures are not going to work very well in a cloud. Because cloud is distributed, because a cloud wants to be sitting on top of a bunch of, it's like building a house on a sand pit. And you have to figure out how to deal with building a house on a sand when you're in the internet or when you're in the cloud. So the other area that I want to talk about is infrastructure as code, because that's sort of part of this, how do I deal with the whole cloud environment, because that's what it is. It's infrastructure as code. And you can do it internally, but eventually you're probably heading towards some mechanism of cloud. Containers, as there's going to be a lot of talks about containers, at least one or two, I won't talk about those today, but containers are the thing that creates a process which allows your development to be easily put into a secure, standardized mechanism, so when it's deployed, you don't have to worry about any of the downstream stuff. ThoughtWorks likes to call containers a process that allows you to have a standardized environment. And then there's serverless architectures, and I think there was talk about this yesterday. Serverless is my kind of thing, because remember what I did when I was doing software development was I was programming pieces of equipment. And we didn't have this, I mean, our equipment sent interrupts, and we waited to listen to those, and we responded to them. It was an event-driven environment, which to me is a really comfortable place to be, but to a lot of programmers who are used to procedural programming, it's kind of, what's this all about? But the idea of being an event-driven environment is really important when you get into the Internet of Things. And most people that are involved in serverless, when any type of sort of variation in response to stuff out there in the world, is finding that it's a massive economic advantage not to have stuff sitting there waiting for events to happen. It just costs a lot less. And then software-defined networks, so forget the network hardware anymore. There's a really interesting paper by Google just recently out on how they structure all of their networks with software. No more hardware anymore, because it's just not big enough. It just can't handle the kind of volume that they're heading for. So when you think about that, when you think about where this whole sort of cloud area is going, there's a whole new technology stack you have to learn how to deal with. Back in the 20 years ago time frame, we had a thick client-server app. We had some runtimes and some middleware and some operating system, and then we had some monolithic database sitting underneath it. And today, it's much more like a thin app on a mobile tablet or something like that. Developers will assemble an assortment of the best available services, which will change constantly, and running on whatever available hardware happens to be around. So if you think about that, then the real problem we have in architecture is a dependency problem. The fundamental problem we're seeing in software engineering from our history is we've got this thing called a enterprise architecture. Have you seen this picture, anybody? Some people have, right? It's kind of, I was giving a talk to some enterprise engineers, so I went and looked up what it was all about, and that's what it's all about. And the problem here is that there's this one database that's sort of the magic integrator of everything else. But if you think about it, it's also the magic dependency generator of everything else. That's what it is, a massive, big dependency generator. And so it's a scale-up approach. And if you really want to get big, you can't scale up. You have to scale out to get seriously big. So you need a federated architecture of some sort. Not necessarily microservices, but in any environment at all where you want to be able to get really big, you need to scale out. So you need some sort of federated architecture where the data stores are within the federated architecture, not some central thing that links everything together. So this fundamental concept of a federated architecture is where we have to go in order to get rid of the dependencies that are killing us, delaying our deployments and all of that sort of stuff. And that's kind of the architecture you need to have if you want to move to the cloud. And I don't think, although I'll bet you a bunch of you are sitting on the left side today, I don't think you can stay there. Your future has to be over here where there's some sort of federated architecture. So you need to learn how to do software engineering not with databases, but with APIs, which means they're just every bit as important and valuable and subject to all the kinds of constraints that our databases used to be subject to. All sorts of things like you have to have good hardened interfaces, you have to have good directories, you have to have standards by which the interfaces change slowly, you have to have versioning on changes. It's almost like just a different way to look at the database, but a way that can be localized. So if you think of APIs as architecture, what they do is they enable service architectures. They lower that integration friction because it's only just between me and the other service over there. It's not me and all 50 of those other services. And they have local persistence. So our SQL databases are rapidly being replaced by this stuff that spreads across all of those different files that you saw in Google file structure instead of just one. And we don't worry anymore about we don't have space to put it in our database. We have space. We're going to worry about our database later. It's not, we know what information we need and we're going to put it where it belongs. As you heard just before this talk, we're going to just gather it and put it out there in some format and figure out later how to deal with it and what to do with it. And those are just a whole different concept than the way that we used to think about databases just a few years ago. And you can also think about APIs as a product. So APIs as a product means an API needs to be owned by a team who understands who are the consumers of that API and who focuses on it and who evolves the capabilities of that API. So if you take a look, for example, at anything in the Internet of Things, this would be a Nest thermostat, and it's got an API. And then I can use that API to put a mobile app together on my Android phone and go and deal with my thermostat or my iPhone or whatever. So the APIs are the ones that allow those little things in the internet. They can own an API against which you can put, whatever, and talk to them. So they're a product. And that's what makes them into a product is their API connection to the rest of the world. I find it interesting that Carnegie Mellon, which has always been really big about what do we have to think about in software engineering, in 2014 they came out with an article which is about software engineering for big data systems. And what they said is big data applications are pushing the limits of software engineering. It's essential that the body of software architectural knowledge evolves to capture the advanced design knowledge for big data systems. That's where software engineering needs to be spending time. And if you're thinking about research, thinking about what you do in a university, are you thinking about the engineering necessary for really good big data systems? They said that big data systems are inherently distributed. There's no option. Their architectures, therefore, must explicitly handle partial failures, concurrency, consistency, and replication. And any kind of communication latencies that are sure to occur. It has to be handled in the whole concept of managing big data. They have to have architectures that replicate data to ensure the availability in case of failure. And they have to be able to design components that are stateless because components and instances get killed all the time. that are replicated and that are tolerant of failures of dependent services. So we need to figure out how to move architectural engineering this way, not just for big data, but for sure for big data. So the last thing I want to talk about in this whole area of the cloud is resilience engineering, because now we have huge amounts of things depending upon our software. Like, for example, there were a couple of airlines that went down in the US for like a whole day in July, within 2 weeks of each other. One was Delta and one was Southwest. And they had a little glitch. So Southwest lost a router, and it took them out for a day. And Delta lost an electrical switch in Atlanta. And that's its, home base. And it turns out that in order to fly an airplane, you have to file a report with the FAA, Federal Aviation Administration. And so for any airplane to fly anywhere, this report has to be filed. And the only computer that could do this happened to be hooked up to that electrical switch that failed. So the entire system was down because one electrical switch in Atlanta didn't allow the flight plans to be filed. So where are we going to know when these failures are going to happen if we try to make everything 100% failure-free? We have to start thinking differently. We have to start thinking about anti-fragile instead. So if you want to see more about this, you can read Nicholas Taleb's book. But the whole concept is that there are things that are fragile, like glass, and there's things that are robust, like swords, and then there are things that get better when they're attacked. Like, for example, a month ago, I had a flu shot. Every fall, I have a flu shot. I so put these bad things in my body so that it gets stronger, and I don't get sick much anymore ever since I started doing that. So the whole idea of adding bad stuff to make stuff better is what anti-fragile is all about. So if you look at the classic one of Netflix with their simian army, they do stuff all the time. From small, every 2 hours, I'm going to kill an instance, to I'm going to add latencies, to their chaos guerrilla, which takes down a whole Amazon region every so often, just to see how everything responds. So when you think about testing, you also have to think about, in fact, Netflix thinks about the real test is whether or not your software can survive in production with all these chaos monkeys and things like that, killing instances and making sure that things still work. And the ultimate test of good is whether or not that's the way, the ultimate test of any team's good is whether or not any of their services fail when any of these gorillas come in or monkeys come in and kill them. So to sum up software engineering in the cloud and where I see it going, we gotta move to federated architectures. There's just not going to be an option. It's gonna be cheaper, better, way faster to deploy, and it's gonna be necessary because you're gonna go to the cloud. We have to start thinking about the database, stop thinking about the database as the integrator anymore. And I'm still reading stuff in McKinsey and Gartner about how the database and the ERP system is the integrator. It's got to stop being the integrator, okay? That's like so last decade. We need to think about how we connect with APIs across multiple different concepts of the way we store data. We have all these stateful protocols, but when we start getting into anything that's going to be out there like the Internet of Things, we have to think stateless, because when you get on the cloud, stuff dies all the time. And it will lose state. So what are you going to do about it if you're depending on it? We have to stop thinking about consecutive execution and think about stuff happening concurrently, and we don't actually know which race condition is going to win. I can remember that race conditions were one of the biggest things I had to deal with when I was programming equipment. And you always thought about which one's going to get there first. You don't know. So instead of synchronous communication, like talking on a telephone, we have to figure out how to do asynchronous communication, like text messaging. Okay? The other person doesn't have to be there until they get around to answering your text. We have to figure out how to do event-driven programming. As I said, to me, that's like natural. because it was the first way I thought, well, maybe the second way or the third way I thought about programming. But when you have big pieces of equipment, it's just kind of very obvious. But I've been told it's really hard for people to think about event-driven programming. Well, trust me, it's not so hard. You just got to switch your mind a little bit. Instead of procedural programming, and we have to start thinking about, forget about defect-free, because that means we're fragile. We have to think about when stuff happens, how resilient are we? How fast can we recover? How small can we limit the blast radius when stuff goes down? Because it's going to go down. So this is like an artifact of the enterprise legacy stuff. And this is more like what you've got to do to be involved in the Internet of Things. And when we get this stuff working right, then we're going to be much further into the future than we were. Now, it's not the end of my hour, so I'm going to continue on with something else. But it's about the same thing. So this is Germany. And I've been told, actually, I've observed that people like process in Germany. So this whole, whoa, how do we deal with all of this uncertainty becomes, what process can we apply in order to get our hands on this? So I would like to talk about DevOps. This is a book that's not a month old, and I actually am not sure you could get your hands on it yet. I've got my hands on it, and I read through it, and I like it a lot. It's by Gene Kim and Jez Humble and Patrick Dubai and John Willis, and it's about the 3 ways. Gene Kim wrote the Phoenix Project about DevOps, and this is sort of like the handbook behind it, lots of how-tos. And in it, they emphasize these 3 ways. The 3 ways are flow, feedback, and experimentation and learning. So the other part of this talk is about flow, feedback, and experimentation and learning. Because if you're going to make this stuff work, you have to figure out how to make that process work. So there's one thing that we know for sure, absolutely for sure. When we have a complex system, it doesn't matter if it's a weather system or a heating system or a software system. Here's something that does not work. When you take a complex system and you smash it, you have no idea how it's going to respond, guaranteed. All bets are off. You don't know the interconnections, you don't know the unintended consequences, you don't know exactly what's going to happen. And try as you might to test it, you can't figure it out. So what does work? What works for complex systems is this. And there's an awful lot of experience showing us that this is the way to make sure we have secure, stable, complex systems that don't crash, is we poke them instead of smashing them. And we respond to whatever happens with that small contained poke. So because of that, sort of the landmark thing that happened in 2010 is Dave Farley and Jez Humble's book on continuous delivery. And if you haven't read it, you should, and maybe you should be going to Dave Farley's talk if you haven't heard it, because this has changed the way we think about software development process. It's just had an amazing impact, and this is pretty much the process you need to be thinking about if you want good, stable systems. So what is this all about? It's about making sure that your process is driven from acceptance tests that are executable and that you write code to pass those tests. It's about making sure that you have cross-functional or full-stack teams that include the full stack of people necessary to do that particular thing you're trying to do. Product has to be there, QA has to be there, ops has to be there, a few devs too. It's about automated everything, build, testing, database migration, deployment, you name it. It's about deploying to the trunk. It's about having no branching. How many here have branches? Okay. Then you're not actually here yet, but it's about not having branches. Wow. Now, if you have 30, you get to 3, you've made a big step. But in the end, you want to have one single trunk that you're continuously integrating to, and that software is always production ready, or you get it fixed right away, top priority. Sound terrifying? That's where you need to go. And you deploy all the time, constantly differing by domain, but deployment and release are not the same thing. You release by turning something on with a switch. You deploy all the time. The code does not have to be live until you turn it on, but you deploy it constantly. So if you think about that as a deployment pipeline, what you have is something that's going to be faster, it's going to be safer, and it's going to be better than what you had before. And this needs to be the process you think very hard about heading towards. The second piece, remember the 3 ways: flow, feedback. The next one is feedback. And I propose you need end-to-end feedback. You need, yes, to see what's going on in production with monitoring systems, but you also need to see what's going on when the code is deployed with your consumers and get that fed back straight to the people who are making decisions about what to do next. Who had better be on the team, because this is a fast process. So we don't have any more outsourced design. There's research to show that the product manager is wrong at least half the time. And I put the reference down here. You can get these slides and look it up. And actually, if I talk to product managers, they say, yeah, actually, this is true. So how do we not do everything that we're asked to do? Because clearly, half the time, it's just a guess. Well, it's always just a guess, and you could flip a coin to decide which half to take just as easily. Or if you take a look at a spec that somebody's given you, like a government body or something like that, probably 2/3 of the features and functions in the specification are not necessary, don't need to be there. Okay? And so it's just better to be lazy and only do that 1/3 or less of the work that actually is going to provide value than to do everything in the spec. So we should not be outsourcing design to somebody else that tells our teams what to do. We need to move from delivery teams to problem-solving teams. So delivery teams get instructions, take orders, somebody gives them you give them a menu and they give you the order. And we have to move to problem-solving teams, teams that have everybody necessary to take a problem, not a solution, but here's what the consumers are trying to accomplish. Here is the job that they need to be done. Here's the metric we need to move in a different direction, see what you can do with it. And we need to have problem-solving teams that address that kind of question rather than teams that are told what to do. So if you look at the experimentation and learning process, I promised you a process. Here it is. You start with signals, not requirements. You have a problem statement, not features. You want to focus on what are the problems we're trying to solve, and a problem statement isn't easy. You plan with hypotheses, not estimates. It's not clear to me anymore if you have problem-solving teams what good estimates do. Anybody? You do have to know that you can solve the problem within the constraints, and given that, the rest should be up to the team. Here's my constraints, here's my problem. If you can handle it within those constraints, usually of time and money, then go ahead and do it your way. And so we don't want a backlog of stories, we want multiple experiments we're going to run against the hypotheses. And we don't want guesses, we want analysis and conclusion. So this is the standard, scientific method, the engineering process. And if this process does not underlie the process that you use today, then you should be asking yourself, why not? Because in our world, with our uncertainty, this is the only process that works. Now, scientists have been using this process for hundreds of years. It's actually not such a bad process, but it's time we got there. But one of the hard parts about this process is the first part. What problem are we going to solve, and what kinds of hypotheses are rational hypotheses to check out? So right at the end here, I'm just going to take a couple minutes to talk about a process that I've run into recently. Certainly not the only one out there, but one that I find pretty interesting. And it's called the Google Design Sprint. It was introduced in 2014 at the Google I/O conference, an interesting conference about. It's more a design conference than it is a development conference. And it's a process for figuring out how to prototype and test any idea in 5 days. Okay, which means before you actually code. It's described pretty well in this, let me go through it. It starts on the first day with everybody get on the same page. How do we do stuff? What's the problem we're trying to solve? Here are the issues, here are the constraints. And then on the second day, there's something I'll talk about in just a little bit more, but it's about each individual sketching out quietly their own ideas about how to do it, and then sharing under the guidance of a designer, because it's a standard design process, and then sharing those ideas on paper so that we're not dealing with brainstorming has been proven to make sure that the people who are loudest or most in command of the language or whatever else it is, or the most like everybody else, are the ones who get their ideas heard. So instead, we want a process that allows lots of different ideas from the quieter people and from the people who are not so comfortable talking to get their ideas too. And then there's decide which ones of these ideas, and there I'm going to talk about not voting, because voting, again, suppresses minority ideas. And then you do a very quick prototype. You've got some designers there. They put together something really quick. It's not code. It's maybe Keynote or PowerPoint or something like that. And then on the 5th day, you have a few users come in and actually test out the idea with an interviewer walking them through some stuff, rest of the team watching from a remote screen, seeing how things go, and finding out how that idea plays with at least a few people. So that's the general concept here, and here it is, a book on it where you can get a lot more information, and I'm just going to do a quick video of a summary of it.
In business, development time is a precious resource. Why are you wasting it? To be more efficient and responsive, Google Ventures created the Design Sprint, a process for answering critical business questions in just 5 days. The first day of the sprint is for sharing information between departments and creating a simple user journey. Day 2 is Sketch Day, where the team works individually to generate creative solutions to the problem. On Wednesday, the team looks at all the solutions and decides on the best approach. Create a visual storyboard, and you're ready for Prototype Thursday. It's time to get productive and build your prototype. On the final day, you test your idea on real people to see if it has any value. If it does, high fives, you're onto something great. If it doesn't, well, you've learned something, and the cost is only 5 days. So stop wasting your time and compress the endless debate cycle into a single design sprint week.
So, 2 things about the design sprint I'd like to quickly point out here if you find it fascinating, and one is the idea generation on the second day is really interesting because it's having individuals not compete with each other to get their ideas heard right from the beginning, but allowing those fragile ideas to be developed by individuals slowly until it comes to some detailed thing that they post, and then it's reviewed by the group, well, without even knowing whose ideas are which. Because there's a thing called conformity bias, one of Linda's biases. Yes, Linda? And it's about the idea that people who think they are in the minority will self-silence or change their opinion. And then that makes it even harder for other people who have minority opinions to have opinions. So the idea is to find a way for people to get their ideas exposed before they have to worry about if they're in the majority or in the minority, and in a way that doesn't require them to be the loudest person or the most, forward person, or it's okay if they're a little bit different than the rest of the group. But I don't agree with the way that they talk about doing this the third day, because then people vote. And I'm not actually so fond of voting, you might figure out why. But at 3M, where I worked for 20 years, we didn't vote on product ideas. We attracted people to product ideas. So we explored a lot of ideas, which you should be too, because in the whole lean idea, it's not, don't settle on one idea, try a whole lot of them. And make sure they're from the whole design space, including some outliers, which means if you vote, the outliers aren't going to make it. And so you want to pursue a variety of ideas, and if she has an idea and can attract a couple of other people to try her idea out, why not let them? They don't have to be in the majority. They can just be a few people that try their ideas. That's how almost all of our really innovative product teams worked. If a champion could attract a few other people, the idea got explored until it either didn't work out or it did work out. You gradually narrow the ideas to the ones that are going to work, and you want to maintain multiple options for as long as possible before you settle on something. Don't just choose one thing and go with it. So, to sum up the future of software engineering, first of all, there's going to be a big technical advance that's there. We can see it now. It's about scaling up. It's about infrastructure as code. It's about that whole new technology stack that's sitting in the cloud and having a different way for us to think about programming and think about security and think about reliability and resilience. And then there's the 3 ways of DevOps, sort of expanded to make sure we think about the whole product, not just Dev and Ops, but the whole thing. So we want to think about how do we get a continuous deployment pipeline? How do we put together full stack problem-solving teams? Okay? And make sure that we're doing experimentation and learning all the way through our development cycle. So the future is here, actually. It's just not easy to see, not quite so evenly distributed. But if you look around, you're going to find futures, you know, even in our sessions throughout the rest of the day. So thank you very much.
We have time for 2 questions. If you have a question, please come forth to the microphone. Yes.
Hello.
Hi there.
Thank you for your talk. I have a question regarding the first part of your talk, where you're talking about the trend away from monoliths and more towards distributed systems. I'm afraid that a lot of developers who are looking at what the big companies are doing and who are attending talks like these will then try and solve problems they don't really have and over-engineer their solutions. Like, for example, using Hadoop when they only have a few gigabytes of data, or a small team that deploys dozens of microservices where a monolith may be the more economic choice.
Right?
What do you think?
I think there's never any, here's the final answer, like everybody move here. You need to know where the trend is going and where you eventually need to be. But if you don't have a smart way of getting there, if all of a sudden you think you can jump there without any learning at all, you're almost certainly wrong. So, for example, if you're in a bank, your bank has to be scared right now because there's so much attack on the fees of banks, their basic income, from all kinds of fintechs all over, whether it's mortgage fees or any kinds of fees. So they quickly want to do something, but it's not easy to be quick because the back end is really hard to break apart. And how do I combine it with the front end? So banks tend to have front end teams, and they can do whatever they want, and back end teams that are slow as they always were, which means they can't get much change done because almost everything in the front end depends on the back end. And so there needs to be a solution, but maybe the solution isn't tomorrow we can break everything apart and start over again because we've already got a business to sustain. So you have to figure out how to migrate. And that's going to depend on the context that you sit in. It's not going to depend on how that company over there did something. They're different than you. One thing you can be sure of is if you take that company's solution, it's their solution to their problem. It's probably not your solution to your problem. So you need smart people that can think and figure out, given the trends, what's the right mechanism to get to the proper solution for us in the future. Remember, everything out about Hadoop took 5 or 6 years. At Amazon, the service-oriented architecture took 5 or 6 years. Every one of those things took that long to go from an idea to actually developed at scale. And if you think you can do it in 5 months, you're crazy. It ain't gonna happen. So, you know, stop dreaming. Make sense?
Thank you.
Okay, let's take another question from the app. I have a lot of questions here. I'm sorry I can't ask everything. What do you think about the role of regulation systems like governments or national laws in the cloud federated world?
Well, there will definitely be national government regulations. Doesn't matter if they're good or bad, they are not going to go away. So what I observe is that the people that are sitting in the clouds learn how to understand those regulation systems, learn how to understand the security concerns, and learn how to deal with them. And so that's another reason, however, why I think the cloud will eventually become the thing of choice, because those regulations are complicated to navigate country by country. And if you have your one source figuring it all out, might make more sense. I know in the US a bunch of people are moving much of their personal data to European data servers, cloud servers. Why? Because the laws here are much more protective of individual private data than they are in the US. So if data sits on servers here, it's much more protected by regulation. So the cloud people are figuring out what the regs are and how to deal with them. I think that GE's Predix system is really good at that, and other cloud vendors are learning. So they'll have to figure it out. But clouds can be in a lot of different places, okay? And they will have to deal with whatever the regulations are. Thank you.
Thank you very much, Mary, for this keynote.